All right. Hello, everyone. Uh, Welcome to the second lecture of the series, second live coding session, rather. And today, here's our plan. We have three goals. One, with all the stuff that we created last time, and I hope you have it. Like, if you don't have it, go to the previous lecture and follow it, or rather, ideally, watch it, then re-implement everything on your own. But this code is also on GitHub. So you can also just jumpstart your code from there if you want to, although I don't recommend it. But so now let's use this code in order to create some random networks. That would be goal number one. And then once we're done with that, let's try to visualize our networks. And we'll use a different package for that. So we'll have to install a package, which will be a somewhat weird technical tangent in the middle of this whole thing. And then we will finish with calculating some simple statistics for this network. And this is the simplest statistics is just the degree distribution. You may remember, you should remember from the reading that if you have this, let me draw something. If you have a network, then for each node, you can count the number of edges that it has, and that would be the degree of this distribution. So in this case, for example, for this network, this lovely network, this node will have the degree of 2, because 1 and 2, it has 2 edges associated with that. This node will also have a degree of 2, this node will have a degree of 3, this one will have a degree of 1, and this node, because it's lonely and sad, it will have a degree of 0. And you can imagine that for a bigger network, if you just look at how many 2s and how many 1s and how many 3s you have, it will tell you something about its structure. For example, if you have a network of, say, 100 nodes, and all degrees of every single node are 2, you can pretty much know how the network looks like, right? Think about it. If each node has only 2, it's connected to only 2 other nodes. And let's say also all nodes are connected. So two things. All nodes are connected and all degrees are 2. How does the network look like? Okay, if each node has 2 friends and all of them are connected, the only way to have a network like that is to have a giant circle like made of nodes. I cannot draw 100 nodes possibly, but you get the point. So if all nodes are 2, then you know the network. In that extreme example, let's say you have a network of hundreds of nodes. Oh Lord, I need to, okay. 100 of nodes, all except one have degree of 1, but one node, all except one node have, okay, you know what, I can do math, right? 99 nodes have a degree of have a degree of 1, but one node has a degree of 99. With this information, you can also figure out how the network looks like, right? So there is one node with 99 friends and 99 nodes with only one friend. So obviously it looks like a star, kind of, where you have this one giant super interconnected node in the middle and all other nodes are connected to it, right? So this degree distribution is a helpful thing, and we'll finish with calculating it. All right, so let's do that. Just to remind you what we have now, we have a class called graph, and it has a constructor that makes the graph, and then we can add a node, and we can add an edge, we have a method for adding nodes, we have a method for adding edges, and we have a method for reporting the graph, right? So, and we have a little test case that I can run again. It creates a graph, then it adds a bunch of edges. That's exactly where we ended last time. We add an edge from 0 to 1, and the way we build it is that if, and while adding an edge, we mention a node that wasn't created yet, hasn't been created yet, it creates this node. So as we add an edge from 0 to 1, it actually creates nodes 0 and 1 and connects them. Then we create an edge going from 0 to 2, and then we create an edge going from 3 to 4, and then from 4 to 5, and then I have a separate line that creates one node only, not an edge, but just a node, 7. And when we run it, and we look at the graph, we have a graph of 7 nodes, and indeed 0 is connected to 2 nodes. Yep, 1 is connected to 1 node of 0, 2 is connected to 0, 3 is connected to 4, 4 is connected to 2 nodes because it's mentioned 2 times here, and 5 is connected to 4, and 7 is this lonely sad node that has no friends, right? Okay, so that's where we are. Let's create a random network. So let's make a new cell, and let's make a network of, let's start with a small network of 10 nodes. So let's create a new variable called n, which will be our constant, and that's just the number of, okay, n is probably number of nodes, n nodes. Let's make it like that. I think actually the good practice is to make constants all caps, all capitals. So let's follow the best practice. Okay, so how to create a random network? What is a random network? Well, how's about we create a network of 10, a graph of 10 nodes, and then we connect them with edges, right, randomly. So every time we add an edge, we will just pick 2 nodes at random. Does make sense? So how many edges do we want to have? N edges. That's another parameter. Let's have the n edges equal to n nodes. It's just, I mean, you can have more edges, you can have fewer edges. Let's just look at networks that have the same number of edges as the same number of edges as it has nodes. So in this case, it would be 10 nodes, 10 edges. Okay, g equals graph. We create our object for a graph, and then we have 2 interfaces, add node and add edge. Okay, so let's start with just creating all the nodes. For I in range n nodes, so I will be an integer that will go from 0 to n nodes minus 1. Let's just add a node with this value. G add node I. Right? And in the end, let's print our graph. So if we do that, okay, we have a graph of 10 nodes and it's empty. All the nodes are there, they're all empty. Sure, that's what we wanted. So now let's add some edges. For I in range n edges now. So let's add an edge. From what to what? From one random node to another random node. Aha, so we'll need a random numbers generator. So let's do here, let's go here and do import numpy as np. Let's run it, and we'll need it because it has random numbers. Okay, n1, this will be node number 1, equals np random rand int. So we need to tell the low and the high, right? Low equals 0, high equals, what's the highest node that we can have? The highest node is n nodes, right? So actually, the highest node that we have is n nodes minus 1, because we start from 0. But the way this parameter works, it also gets, it doesn't expect you to tell it the highest value that it will return. It expects you to give it the value that limits all values from above. It's like weird, but let me remind you, we had it and we discussed it in class once. np random rand int high equals 1. Oops. Low equals 0. Okay, yeah. So if you run it, you can run it as many times as you want. You will always get a 0, because rand integer, that is, because it returns numbers that are smaller or equal to low, but smaller than high. So it was a long explanation, but basically that's why we need to put n nodes here and not n nodes minus 1. All right. Okay, so that would be one node, and n2 equals another node, and p random rand int low equals 0. Basically same thing. High equals n nodes. Right, so let's look at what do we got. Okay, right, so we have some random numbers, right? 4 0 0 5 6 0 5 8 and so on. Okay, let's connect them. So instead of this print, we'll do g, which is our graph, add edge, and if you look at how we wrote it, it expects us to tell it the first node and the second node, right? So let's do that. First node, second node. Okay, look, we have a graph. We have a graph of 10 nodes with some edges, and supposedly it's 10 edges as well. So 0 is connected to 7, 7 is connected to 4, oh no, 6 is connected to 4. 0 is connected to 7, 7 is connected to 8, and also 0, and also 6. So this seems to be working. Okay? So we now have a random network. There are two things that we can do about it. Two things that we haven't discussed, we kind of glossed it over. If you look at those, like if we again look at the values, we actually have some funny things. One thing that's funny is that sometimes we get the same value both for n1 and for n2. So we get edges that connect the node to itself. And we talked about that. It's called a loop. And you don't always like it. I mean, we don't always like it, because if the network is supposed to be a network of like interactions people had during the coronavirus pandemics, then an edge like that doesn't make sense. I mean, everyone have this edge, but which is why it doesn't bring anything new on the table. So maybe we don't want edges like that. So one option could be to just like every time you roll basically the die and you get the same number, you roll it again. It's not the nicest solution, but it is a solution. What else is weird here? Another thing that's weird is that, like, maybe if we rerun it several times. Okay, let's make a smaller graph. See, for a smaller graph, sometimes we have the same edge 2 times. And because we had the same edge 2 times, even though this graph is supposed to have 5 edges, actually it only has 4, I believe. I mean, it should have 4 because one of them was double counted. So 0 is connected to 1, that's one edge. 1 is connected to 2, that's another one. 1 to 0 is counted already. 2 to 1 is counted already. 3 to 4 is another one. It has 3 edges. Oh, right, because 4 to 4 is a loop. So it has 4 edges. One of them is also weird. It's a loop, so only 3 normal edges. Well, for a big network, it will be less of a problem because the probability of getting the same edge twice will be smaller. But technically, like unless we fix that, we won't have exactly n edges. So, all right, let's fix that. How do we fix that? We kind of cannot use for then. Okay, so let's add edge counter. We cannot use for loop because what we essentially want to do is the loop to run until it has enough edges that, like enough good edges, where good is like not repeating and not loops. So edge counter, let's just remember all edges that we created. Edges equals nothing. I mean empty list. So instead of for, let's write a while loop. While length edges is smaller than n edges, which is how many edges we want. So new edge equals n1 and 2. New edge sounds good, right? New edge. So new edge is that. Now, if new edge not in edges, so if it's really new actually, then let's add it. Let's print it for now, we'll delete it later. Oh yeah, another thing, if new edge not in edges and also n1 is not equal to n2, which is an important part, then what? Then we add it. Yeah, that's it, right? So if the edge was good, it will add an edge. If the edge was not good, it will just skip this part, and the length of edges, oh, I also had the typo here, edges, the length of edges won't change. Oh, I have a typo here as well. The length won't change, and it will continue looping until it gets everything correct. Okay. Not white, but while. All right. All right. Here that was a little bit weird. So with 5 edges, ha 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 ha. With 5 edges is actually pretty hard. What? So the problem with this script in general is that it's really prone to there is no way to tell whether the loop will ever find the edges. So if you try to find too many edges in a situation when there are not enough, like if you try to find 5 different edges in a graph that only has 3 edges, it will just run forever. It has no way to tell that you gave it an impossible task. But for 5 nodes, we should be able to find 5 edges. So why do I have this weird thing here that I had to stop it? Oh yeah, right, because I never added the edge to the list of edges. Smart me. Okay, edges, append, new edge, right? Yeah, probably new edge is like, let's get rid of it. Let's just write it explicitly like that. Okay, now it should work. Yep. Okay, so I ran it here for 5 for a graph of 5 nodes, and I asked it to find 5 edges, And I also asked it that these edges wouldn't be loops, so wouldn't be connections of the node to itself. And it looks like it managed to do that, right? There are no loops here. There are no connections of the node to itself. And all of the... not all of the edges are different. Oh, God. Not all of the edges are different. Look, we have an edge 0, 1, and we have an edge 1, 0, but this is actually the same with the same edge. So, how to fix that? Din, 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 din. We can just let's make sure that n1 is all. So let's pick two nodes at random. Again, it's not an optimal solution, but it will work. So let's pick two nodes at random. But then if we want n1 to be smaller than n2, so if it so happens that n2 is smaller than n1, we will swap them. If n2 is smaller than n1, let's swap them. And Python is funny because in Python, I think you can write this thing, n1, n2 equals n2, n1. In many languages, you cannot do that. You cannot swap two variables with one line. Let me actually test that. A equals 1, B equals 2, AB equals BA, print AB. 2, 1. See, they got swapped. A is now equals to 1, and B now equals to... No, A now equals to 2, so the former value of B, and B now is now equal to the former value of A. So, success. It works. Which means that this bar should work as well. Every time... So once we pick two random values, every time one of them is smaller than the other, every time n2 is smaller than n1, we will just swap them. Let's run that. Okay, so now we can see that indeed, all of them are different. It's not obviously a convincing test. What would be a convincing test? Let's see whether we can find 10 edges in a graph of 5 nodes, because a graph of 5 nodes only has 10 edges if you don't count self edges. Remember, I drew it like it looks like a weird pentagram. If you imagine 5, that's 5 nodes, so each node is connected to every other node like that, and also as a star. So we should be able to find 10 edges, but we will never find 11. Okay, let's look at that. It did find 10 edges, but if I ask it to find, oh, it did, what? Okay, when I asked it to find 11, it went to the infinite loop. Good, excellent. That's what we always wanted. Awesome, so back to the story. Let's turn n nodes back to 10. So 10 nodes, 10 edges, no loops. We have a graph. Everything works. Good. Awesome. We can create random networks now. Because now with this thing, you can put 100 here, right? And you'll have a network. Let's delete this thing. We can have a network of 100 nodes. That's how it looks like. Node 60 is connected to node 3 and node 32, which is encouraging but not very helpful. But look, some nodes have lots of connections. Some nodes have no connections because we pick them at random. So it looks like potentially it may be a random network. But at this point, with networks of this size, we can no longer rely on this text output because, like, yeah, how do you even understand whether it makes sense? So we need to find a way to visualize these networks. And we will visualize it using a different package called networkx. And I don't remember whether it's installed by Anaconda by default, but I would assume that probably that's not necessarily the case. So Let's go and install it, and I'll have to share my entire screen for this to happen. Okay, so now supposedly my entire screen is shared, and among other things I have this Anaconda navigator. Oh, probably my face disappeared. Let me bring my face back on top. Because presumably it adds a human touch, right? And we like human touch in this touchless time. So here's the Anaconda navigator, and if you go like this is home, these are the programs that I installed or not installed, like Spider is not installed. And then on the left there is a thing called environments, and you should probably have only one environment. I have two for some reason. I mean three for some reason, but you probably have one called base root, and you can click here and you can click open terminal. And here you can do something like conda install network X. And if you do that, then some magic happens. We're witnessing magic right now. And in my case, all requested packages are already installed. But in your case, maybe something will happen, and maybe it will ask something, and you will have to tell it yes by pressing yes and entering, like pressing the enter button. And eventually you will have network X. So if it doesn't work, we will be in touch one way or another, either through Piazza or we'll have some virtual office hours on Zoom, I'm guessing. But in which case we'll fix that, and then you'll return to that and do the network X part of the story. But let's assume that you have it. So let's assume that this worked, and you typed exit, and it exited, and we can go back to we can go back to our Jupyter. Okay, so let's do it 10 nodes once again. Let's clean up a little bit. We don't need this thing. This was for testing. We don't need this thing. It was for testing as well. And what else? That's good, right? So what we'll need is we'll do import network X as, I think not that many people work with this package, but those who work like to shorten it as an X. So let's use this thing. Let's actually move this entire thing upwards. So I press X, it disappears. I go up, 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 and then I press V, and it reappears here. So let's run that. Now supposedly I imported network X as a package. All right. So the way network X works, network X draw. We should be able to create something like that. So we should be able to create various diagrams that show the actual shape of our graph. That's what we want, right? So let's figure out how to do that. Network X draw. Okay, drawing. Network X 2.4 documentation. Drawing. And then we see there are several ways to draw it, probably with several different, like, look, it looks like this one is called matplotlib, so probably it relies on some matplotlib functionality, and then there is some other type of drawing called graphviz, agraph, and something else. So let's probably, just because we worked with matplotlib before, let's stick with it. And let's see, so there are different, as you can see in this table, there are different methods here. and all of them look like draw underscore something. So it looks, we can draw a graph, and this is the basic method, but we can also draw it in different ways. We can make it circular, and we can make it spring and shell and whatnot. I'm not yet sure what some of these options mean, but one thing that we can notice is that it seems like it wants to get a G as a graph. So network X wants to have its own graph object. We created our graph object, but in order to make it plot for us, we need to create its graph object. So how to make it happen? Oh, look, for example, here's what it can do. It can do G equals nx dodecahedral graph, and then we can draw it. All right. Sure. So, but we don't need a dodecahedral graph. We need to create our graph. So maybe let's just Google network X graph create graph create. Network X create graph, creating a graph, documentation. Good. Okay, so to create an object, we do G equals an X point graph. Sure, we can do that. Then look, it has G add node. So it's kind of, notice that the methods it has are pretty similar to what we implemented, because it's a kind of rational way to make it. I mean, to work with graphs, but we want to use our graph object, but we will have to translate it into this graph object. And we want to use ours because we'll add different types of functionality to it, right? But so for plotting purposes, we'll have to create this network X type object, and it looks like we can add nodes, but what's more interesting, we can add nodes from, so we can give a list of nodes, and it will create all these nodes. And this is about nodes. Can we add edges? Yeah, look, we can add edges as well. So we can add one edge, exactly like we do, notice that. But we can also add edges from. And what, like, here, if you look at what's written here, it's a list of tuples, because the outer brackets are square brackets, but the inner brackets are round. So this is a list of two tuples, 1 to 2 and 1 to 3. But if you read later, it says that it actually fine with any iterable container of edge tuples. What does it mean? It means that if you go upper for nodes, we can actually find a similar sentence, and it has a little clarification. It can be, so for nodes, as for edges, it can be any iterable container, in this case of nodes, in that other case of edges, such as a list, a set, yeah, or something else. So a list or a set or something like that. A list of nodes, for example, is a good option, right? We can also have a set of nodes if we want to, or a set of edges. Okay, so that's enough. We know what to do. So we need, of all these luxury, we need three things. We need this part, G equals an X graph. Let me go back. Oh yeah, let me go back here. So let's just create a new cell and do G. I don't like large G, so let's make it what? G and X equals an X graph. I think that's how it looked like, right? G equals an X graph. And then we'll be able to do G adds nodes from and G add edges from. Okay. So we will have g add nodes from, and we'll have g add edges from. And here we have a list of tuples, but we are not actually ready yet to do this stuff, because from our graph that we created above, we don't have an easy way to extract all edges from it, or extract all nodes from it. Here we actually created a list of edges, like, to be fair. So we now technically we have this information at this moment, but we don't store it anywhere. So for this graph, for example, even though we created it, we didn't have access to a list of edges. So what can we do? We have two options. Either as we create the graph, we will keep the list of edges, we will store it as just another property, in the same way as we store the dictionary that describes the graph here. Or another option, we can write a method that will create a list of edges for us. And this is probably better, and also it will give us an opportunity to think about how to make it in Python. So let's do that. So let's make two more methods. First, let's do the simple part. Nodes self. So this method just, and I will write a documentation string, returns a list of nodes. Let's do click. Yeah, it's fine. Returns a list of nodes. How to return a list of nodes if all we have is a dictionary and nodes are used as keys of this dictionary, because that's what's happening now here. It turns out, and if you went through the textbook, you actually read about it when you worked with dictionaries. A dictionary has a method called keys. Let me illustrate it somewhere else. So A equals a dictionary 1 dog 2 cat. How does A looks like that? So A has a dictionary. A has a method called keys that returns almost a list, except it's not a list, but it's almost a list. And we can make it a list. But it has all the keys, and to make it a list, we can just write list around it. There is a small difference between like what it returns and the list, but we kill this difference by wrapping it around with this command. Yeah, so we can do this for any dictionary, and you will have a list of its keys, and that's what we need here, because that would be the list of nodes that we seek, that we want to have. So return list our dictionary, which is called self.gdict.keys and parentheses. So let's delete this part. Let's test that for our old graph that we created manually. Print G, so print G nodes. Oops. Oh yeah, because I forgot the parentheses. Oh, look at that. We have a list of nodes. We have nodes from 0 to 7, which is what we want. Nodes. This is a test, and the test shows that our new method works great. So now what we need now is a similar method that would create a list of edges for us. All right, we can do that. Define edges self. So very similar, and it will returns a list of edges. Now the question is, do we want a list of edges or a set of edges? Because network X can work with sets of edges as well. But let's use a list for now. It doesn't matter that much. Okay, here we cannot do a one-liner, because what we need to do, we need to go through this dictionary here, and we need to go through every node. And for every node, we need to look at what it is connected to and make it into an edge and add this edge to a list. So we need to do kind of in the opposite, in the reverse direction, everything that we did while we added edges to the graph. And again, technically, you can cheat, we can cheat, and we can, instead of doing that, just save all the edges when we do the add edge operation. But let's not do that, because right now I'm not quite sure. Maybe we will change the graph. Maybe, for example, some people will stop being friends with some other people for some reason. So it's good to have this method implemented honestly and not just, have two different structures that are supposedly matching, but that nobody checks whether they actually match. So let's do this. Returns list of edges. We need now to iterate through all nodes in our dictionary. How to do that? It turns out that it's pretty easy. And there is a really nice way to do that, which is for key value in dictionary, which in this case is self-gdict. And what will happen if we do that is that key will take all values of keys. So if for this particular dictionary, key will be equal to 0, and then 1, and then 2, and then 3 for every turn of the loop. And there will be 8, right? Is it 8 or 7? Oh, 7, because we don't have a node number 6. Like, that's weird. So 7. It will iterate through all 7 values and the key, and the value for each of those will be equal, will be set to the value that is stored in the dictionary for this key. So when key is equal to 0, the variable value will be equal to at least 1, 2 for this particular graph. When key gets equal to 1, our value will be equal to a list that contains one element of 0, and so on. All right. So for key value in self dictionary, I don't like these names. So let's call it like, because keys here are nodes. So for node, and value is like a list of nodes to which it is connected. So maybe let's call them links or something like that. For node and links that take values from the dictionary, what do we do? Basically, we need to create a list of edges. So let's create an empty list. Edges equals empty list. So basically we need to do edges append, which adds a value, and let's add an edge, and that edge will go from node to a link. Oh wait, we don't have a link, we have a list of links. Okay, so we need another loop here for link in links. Right? So what will happen is that we'll go through every element in the dictionary, and then for every element, for every node, we will see the list of nodes to which it is connected to, and then link will go through all elements in this list, and then each of them will be added to our list of edges as a new edge, and then we will return edges. Return edges, right? It kind of makes sense. It's actually not quite correct yet, but okay, let's try that. Why not? So as usual, let's go down and look at our test case and add here print edges, g edges. Okay. Okay, we have some sort of an error. What? Cannot unpack non-iterable int object. Uh-oh. Oh, it's a bad idea probably to have this thing named in the same way as this thing. Is it that? Okay, let's rename that into out. That's wrong. Like this variable, this list will be called out. It doesn't help though. Oh, right. Oh my God. Oh my God. I'm so sorry. When I told you that there is a nice way to work with dictionaries, of course, you don't just do in dictionary. You do in dictionary items and also brackets there. Items. For any dictionary, every dictionary have this method called items. Is it a method? Probably a method that gives you these pairs of node its value, node its value. But it's, yeah, so this is the syntax that we want. All right. Let me show you how it works in a small example here. So again, A is a dictionary that from 1 it goes to dog, and from 2 it goes to cat, and then it works, and then for key value in A items, print key value. Yeah, so it seems to be working, right? I just forgot this items thing, but now it works. Key gets equal to 1 and then to 2, and value gets equal to dog and then to cat. All right, so maybe now this thing will work. Oh yeah, look at that, it actually works. So you can see the output here. Oh Lord, okay. You can see the output here, and the output looks like edges. It's a list of edges. There is an edge from 0 to 1. Yeah, we want it. And then edge from 0 to 2. Yeah, that's great. And then there is an edge from 1 to 0. Wait a minute. We definitely don't want to have that, because this is the same edge as 0 to 1. Uh-oh, we have an issue. So what to do? We actually had a very similar issue just recently, right? When we connected things randomly. So what can we do? Basically, we need this line, out point append node link, to run only sometimes, only in half of the cases. So when 0 is connected to 1, we should run this line. When 1 is connected to 0, we should not. How to do that? Okay, let's do the following. Let's just only add those edges where the left node is smaller than the right node. The number of the left node is smaller than the right node. So if link is larger than node, then append. So let's think about that. For every node, so we don't consider any loops. So connections between the node and itself, we just ignore them. We pretend that they don't exist. We don't allow them actually during the random network creation. We can still create them manually, I think, if we use the interface, but let's pretend that they don't exist. We can also prohibit them if it gets to that. But so if they don't exist, then it's always one node to another node. So there are always two numbers that are not equal to each other. So one of them is always smaller. And as we go through the graph, we'll always encounter every edge twice. First from one node to another, and then from this other node to the one, right? So always there and then back. We'll encounter every edge twice, but only once will be actually from the smaller node to the larger node. When we encounter it the other way, the other time, it will be from the larger node to the smaller node. Does it make sense? If it's like 1 connected to 2, we'll meet 2 times. 1, 2, and 2, 1. And so let's agree that we only include 1, 2 here. So only cases, let me rewrite it, only cases when node is smaller than link. We could have done it the other way around, it doesn't matter. But what it will, so once we add this requirement, now supposedly every edge should be only included in the list once. Let's test that. 0 to 1, yep. 0 to 2, yep. 1 to 0, 2 to 0 are not included. Good. 3 to 4, yep. This part. 4 to 5, yeah. Again, 4 to 3 is not included, 5 to 4 is not included, and 7 is not included because 7 is a lonely node, it doesn't have an edge. Okay, great. So we have edges now. So basically, we are ready to create a visualization. So maybe at this point it would be good to pause the video. I hope you pause the video, by the way. The coolest thing, once I upload these videos on YouTube, the coolest thing is that you can change the speed of the video up to like 25%. I mean, 125% of normal speed. So I will be speaking faster like that, and all the awkward pauses will disappear. But then you can kind of fast forward through my explanations, but pause when you need to do something or when you need to think. So this would be a good point now to pause and make sure that you implement all of this stuff, the part that outputs nodes and the part that outputs edges, and you need to test it. And then we can get here and we can create the graph. So we created, okay, so the part that creates the graph, G and X. The first line just creates a graph. Oh, by the way, I remember we had a way to number the lines. So the first line just creates the graph, the object. The second line will add nodes from where? From our newly coded G nodes. And the third line will add edges from G edges. And then once this is done, then we will visualize it. So let's go back to this part and visualize it. For example, let's do what? Which one do we like? Let's do this Kamada Kawaii. Just because I know that it kind of works. Okay, this one, select, go back, NX Kamada Kawaii. Maybe we can do just G and X, I think, right? G and X, draw Kamada Kawaii. Okay, that didn't work. Okay, no. We do NX, Kamada Kawaii, G and X. Oh, look at that! We have a plot, and this is not a random graph because I haven't rerun the creation network recently. Is the graph that the manually created graph. So let me actually copy that and add it here. Okay, let's see whether it matches. So if we look at this graph, we have nodes 1, 2, and 0 that are connected to each other. 1 is connected to 0 and 2 is connected to 0, so it should be triad of nodes. And then 3, 4, and 5 form another triad. And then there is a lonely node number 7. And look, that's exactly what we have here. We have 3 nodes and the lonely node. So it actually seems like it works. Okay, let's try that with the random network. We'll rerun the random network and then we run this thing. Oh, look at that. I mean, if you have this same code, you won't necessarily have this spaceship. Because let me rerun it again, this and this. See, that's a different spaceship. So, but we seem to be getting various types of random networks. Right? Okay, let's make a funnier network of like 50 nodes. 50 nodes. It's large now. It's hard to print now. Let's not print it. Let's just visualize it. Look at this spider. The nodes are probably a little bit large. So can we deal with that? Can we make like them nicer? Let's go to draw again and let's click on the basic draw and see what parameters does it take. Does it take anything interesting? Oh, Okay, so no parameters here. Let's network x what? Draw marker marker size, maybe marker size. Okay, node list, edge list, node size. Look, node size, scalar, one value, or array, lots of values, so we can make them of different values if we want to. Default equals 300. Okay, let's make it node size, let's make it smaller, let's make it like 100. So we supposedly we're adding it here. Node size equals 100. Oh, look at that. We have a smaller network, right? So we have all these nodes and they're connected, and then there are also a bunch of nodes that are not connected, and they're sitting in the middle of this thingy. And yeah, they're not obvious, but they exist. They just sit in the middle. All right. So we have this tiny script. I kind of don't like having it here. So let's maybe move it into a method. So let's copy this entire thing and then go upwards, upwards, upwards. And let's make it a method kind of similar to how we already have a method string that like makes it a string. But now let's make a method that plots it. Define plot self. And we copy all these four lines, and the only difference is that instead of G nodes, we should now do self nodes, because it's now about this object. We're writing a method for this object. So self nodes, add self edges, and yeah, then plot it. Okay, let's try that. So here we add G plot. Let's run it. Yep, worked for this one, and hopefully it will work for the random network as well. Yep, worked for the random network. This can be deleted. Nice. Now we can plot stuff. Okay. And this is the end of part 2. So part 1 was creating a random network. Part 2 was visualizing it, and we had to write some transformations for that. We now have a method that generates a list of edges. And now part 3. And part 3 is a part where we look at some basic properties of this network, and the basic property is the distribution of node degrees. So for example, for this nice plot that I have, can I like copy it somewhere or something? Done. Yeah. Oh, look how nice. I can copy images to this whiteboard. Except now okay, whatever. Let me delete some of the stuff. So let me delete that. Let me move the image here. So for this node, the degree is, how many friends does it have? 1 friend. So for this node, the degree is 1, right? For this node, the degree would be 2. For like this node, the degree will be 3. So this 1, 2, 3. And somewhere deep there, like this one is 4. Can you see that? And then there are some 0 degrees as well. Like this one was 0. So it has some variability. It has like this node, this node. Its degree is like 6 or something, I think. So let's calculate all these numbers. How to do that? Let's go back and again, oh no. Again, let's create a new cell. So the general kind of strategy is that we usually create, at least that's how I like to work, but I think most people like to work like that. You create a new cell and you just write some strange code there. Once it works, so once it kind of works, you make it a method in a class. And one thing that we haven't done yet, but we may do it later, I'm not sure, we may have to. Once your class becomes kind of bulky and it's several screens of code, and it looks like you're not changing it anymore because it kind of settled down, then you can take it out of the notebook and make it into a Python script or Python module, rather, Python module. So one of those files with py extension. But we're not there yet. We're still we're messing with it a lot. So, okay, let's calculate the degrees. How to calculate the degrees? Let's do this thing again that we did before. For node links in G, was it like gdict or something? How is it called? Yeah, gdict in one line, in one word, without underscores. In gdict items, print node links. Yeah. So here's the kind of printout of our dictionary that describes the graph, right? So what, instead of the actual links, the actual nodes to which each node is connected, we only want the number of links it is connected to. So instead of links, let's do length of links. Yep, look at that. So we have some 4s, we have some 2s and 3s, and we have a 0 and occasional 0. What's the biggest one? We have 5. We have 7. Look at that. Node number 19. I mean, in your case, it will be a different one because it's a randomly generated graph. But you can have something. You can have up to 7. All right. So now we need to make a histogram of that. So let's make a histogram. Let's make it manually. How to make it manually? Let's create a variable called hist. And here, like, do we want to use lists, or is it time to switch to NumPy? What's better? Doesn't matter. Doesn't matter necessarily. But we will probably need NumPy anyway. So let's go upwards and also import num. Oh, we actually have NumPy. Oh, we will need. You know what we will need? We'll need matplotlib because we'll want to plot this thing. So let's do that. Import matplotlib pyplot as plt. So let's do that just in advance. Now we go back down, and histogram will be numpy zeros. So how many? It should be from 0 to what? In this case, to 7. But maybe in some plots it will be less or more. So let's just go. Okay, let's do the following. Let's first populate a list of all possible. So let's wait with this histogram thing. Let's wait it. Let's wait with it. Let's first create a list of degrees. Degrees will be equal a list. And instead of printing this thing, these lengths of links, let's append them to the degrees. Degrees append this thing. So what will happen is that the loop will go through every node, and for every node it will have a list of nodes it's connected to. It will look at the length of this list, and it will put it in the list called degrees. So by the end of the story, if we do print degrees, yeah, that's what we have. See, here's our 7. Here we have some zeros. So this is the data that we need to process. Okay, so now once we have done that, now it's time to create a histogram. So histogram is zeros. What's the biggest value? The biggest value is maximum of degrees, right? So actually we'll need more. So think of that. We'll need one more because here the maximum degrees is 7, but the smallest degrees is not 1, the smallest degrees is 0. So if the biggest degree is 7 degree in the graph is 7, then we will have everything from 0 to 7, which is 8. So it should be np0's max degrees plus 1, and then we do 4d in degrees. Well, degree, let's be civil. 4 degree in degrees, hist degree plus 1. Print histogram. Seems to be working. Look at that. We have 6 zeros, we have 14 ones, 14 twos, 10 threes, and like 4s, 5, 6, no 6, but 1, 7. So there is somewhere here one node with 7 connections. For some reason I cannot see it. I'm not sure which one is it, but maybe it is this one that looks like 6 but is actually 7. I'm not sure. Anyways, we have the histogram now, so let's plot it. We printed it. PLT plot. So if we just do hist, it may work. Will it work? Yeah, it kind of works. Oh, it actually works. It's actually what we need. We don't even have to mess up. We don't even have to create a fake x-axis. It just use 0 as the smallest value, which in this case is exactly what we need. So that's good. Let's just add like little markers, and let's add some, let's put a semicolon so that it wouldn't write these strange things on the screen. And then let's do x POT x labels, x label, x label, x lab. I forgot how it's, okay, let's try it. Nope, not x lab, x label, yes, x label. So this is like degrees, and PLT y label is frequency. All right, so that's look great. Yeah, so basically at this point we're happy, and we did everything we wanted to do. I will post some homework for that, some similar homework where you'll have to create a random network in a slightly different way and make a nice plot that looks like that. And we have a hailstorm outside. Let me show you. I'm not sure you can see that because the screen is probably reflected in the window, but it's a hailstorm. Anyways, good. I will upload this thing on GitHub. I will post a follow-up for that. On Piazza. Maybe let me describe the follow-up here. So the follow-up will be the following. The follow-up will be the following. I will ask you to create a network in a slightly different way. So a different way to create a random network. Add nodes one by one. As you add it, choose a node to connect it to randomly. Once the network is ready, compare its degrees distribution to that of the truly random network. That was described in the lecture. All right, so I hope it's clear. You take one node, like one node, the first node, the zeroth node, you cannot connect to anything. But then you have the second node, and you pick a node randomly to connect it to. In this case, you can only connect it to one node, to the zeroth node. Then you have the second node, and now you have some choice, and so you pick randomly a node to connect it to. And then you repeat it again and again. So 10th node comes to the play, you have 10 nodes already in the system, you pick one at random, and you add an edge, right? So if you think of it, the degrees of the distribution of degrees should be different, and I want you to think about that. Then code it and check it, and compare the two plots, the one that we basically have here on the screen with the one that you will have for this other network. Okay, done. So cheers. Talk to you later.